Hi, welcome to this section 2E. We'll see now what are system calls and how is it implemented in Linux at a very high level, not at the core implementation level. This will give you an idea of how important it is and how critical when user process tries to get some services from OS. And I said that any OS service has to run in a kernel mode. So how is that happening and how is it made sure that illegally someone is not getting into a kernel mode? So these two are the things which we'll cover now. Now what is a system call? System call is one wherein we call a routine that will take you to the OS. That means OS is providing you some APIs as services and the user applications or any tools or system software that we write, we make use of those system calls to get the services from OS. Now, let us take an example of our own executable, one simple program which we'll be using C library for it. So, a system call is a programmatic way of in a program, computer program, which requires a service from the kernel. That is a system call. We are calling a system from the user application mostly. This may include hardware related services or like accessing hard disk or creation of execution of new processes. You want to create a new process or communicating with the kernel services or something you want to do with the scheduler. So anything that you want services from the OS, you have to go through the system call. There's a strict and well-defined interface for you to enter into the kernel. So system calls provide an essential interface between a process and the operating system, which is a user process to be to be precise. So implementing a system call requires a transfer of control from user mode to kernel mode, which involves some sort of architecture specific feature. Now it depends on the processor on which this particular OS is running. It though the way it is implemented is OS dependent, it is finally has to be modified or fine tuned to a particular architecture. Whether it is a ARM processor or an Intel processor or whatever. So any executable program, if it is needs a services, it will call system call, or through library function also the system call can be called. Okay, there are two ways you can. If you are writing a system software, you may directly call the system calls. If you are writing an application program, then you will use a C library which will in turn may be calling the system call. Finally what will happen, you have to accomplish something, then you need to go through the OS. Then system call itself is an entry into a kernel. So here only the kernel mode comes into picture, and rest of it is will be user mode. The outside of system call is a user mode, and then the hardware is accessed by the kernel. Okay, this is how the path is shown. Now let us see an example system call. A simple example is a printf. Now it is going to call a system call routine, because you are supposed to write something into a terminal or a display which is a hardware. So you cannot do it, you cannot write into a display without informing the OS or without getting the services from the OS. You cannot directly write into it unless you write it, you running it in a kernel mode. So you normally what will happen, we will be using printf, which is a standard C library. And let me show the path, my program, which is calling a, you will be linking it with this glibdc or sd, we will having hash include we will be doing in stdio.h, which gives you the prototype of the library function which you want to use. It doesn't have a definition of those functions, it's only having declarations. This is to inform the compiler that this is the interface signature of a library function. That is what the stdio.h does. Now, having understood this, when you are using the printf, it will verify, the compiler will verify whether are you using it as per the signature of the function. Okay, are you passing the first string followed by some parameters. Some compilers are intelligent enough to map it with the percentage %d and then the type of variable you are passing. It may say that no, these are not matching. Suppose the format specifier in the printf, you are given 3 4, but you are passing only a couple of parameters or less than the number of parameters. Or some printf, some compilers are intelligent enough to give you that you are not calling it in a proper way. But mostly it is meant to only check whether the first string is first parameter is a string and followed by any number of parameters. So the main purpose of including a hash, including any header file is to match with the description or the signature of the function with how it is being used in your program. Implementation is not part of the header file. Now, when does the implementation come? When you are calling these functions, and then when you are building an obj file of this, it is independent. It's not going to have the library file included. But when you are building an executable, the C library is automatically included, and any of those functions that you are using will be resolved during the linking time. And resolved in the sense, whatever function, library function you are calling, it will be mapped to the actual function in the library, and there will be a call to that particular routine made while the linking happens. And then the whole code goes into the executable form file, and then that gets executed when you load it into the main memory. So this is the path. This is how it is done. Declaration is done in the header file, and the actual definition is in glib.this lib or sio or whatever. Then in turn, a system call is made by the library. C library itself is not running in the system mode, kernel mode. It is running in the user mode. It is going to have a system call, which is a write function. And during that time, the transition happens from the user mode to kernel mode, and the actual writing of onto the display will happen. So printf is a library function which in turn calls a C system call, and which is a write function. And the system call, when it is called, transition from user mode to kernel mode happens, and the kernel code, which is a write function, it gets executed. So, and then OS in turn calls the display device driver to write the characters onto the screen. So some of the examples of system calls are create process on Windows, which is forks on Unix or Linux, exit process here, exit here. So there are many things. Okay, even for opening a file, this is some system calls are there on Windows, and different implementations are there, and different function names are there, which are also performing the similar function. And please understand, though they are all performing the same function, their parameters and the type of parameters and return values may be different, and which is very OS specific. So you need to know how to call those system calls, and what are the parameters to be passed in which order, what type, and then how to interpret the result return value from these system calls. They are very OS specific. So all the system calls are, once it is called, and internally they all run in kernel mode, and they perform various operations using the CPU or a hardware, okay, specific function activities. So system calls are not directly called by the user process. Now there is a wrapper function. Okay, it's like when you are entering a president's office, or maybe the VC of a college, then you will not be able to enter the office of a VC or a president directly. You have to go through the executive assistant, and then take prior appointment, and then they make sure that what is to be done by you is well defined, and even the president or the VC is informed about this, about so and so is calling. Here we are not going to call, inform the system call that somebody is going to call. Only thing is, the wrapper function makes sure that correct parameters are passed, and the mode of transition from user to kernel mode happens. That's very important from the system call perspective, the implementation perspective. So one more thing you have to understand, that when you are calling a system call, you will be passing some parameters. So for example, you are doing a fopen. You cannot call the fopen without telling what is the file that you want to open, what is the path of the file from the maybe root directory, and then the name of the file, and what is the purpose of you opening the file, whether you want to write into it or only you want to read from it, whether you want to append it or you want to create a new file. All that operation that you want to perform needs to be informed before, so that OS will call and open the file for a particular activity. If it is only read function, then it will open it for read permission only, with a read permission. So you cannot write into it by mistake. You cannot cheat the OS saying that I want to open the file for read with a read access, but I want to later on, once it is opened, you write into it. It's not possible, because what you guarantee that you will do on it, you should stick to it, because even when you are trying to do it, then OS will catch it, or sometimes even tools may catch it, but it's very unlikely that they will be able to find out. But during the runtime, if you have opened it for a particular purpose and you are exceeding the limit, it will be caught. So this is how this user to kernel mode transition happens, and you will be passing the parameters, and then whether whatever you ask the OS to do, has it been done successfully or not. For various reasons, it could be a failure. For example, the file name that you have entered may not be valid. Then the OS will get the file name. It doesn't know whether whatever you are giving is proper or not unless it goes to the disk and then finds out whether a particular file is there or not, whether you have the permissions to write into the file or not. So all that will come to the OS will come to know only when it opens the file descriptor or the information about the file, like what you have for PCB, which is for process control blocks. Every file has its own descriptor where all the information about who is the owner, what permissions are there for this file, for different users, they're all captured there. So when it opens, it will check all these things and then accordingly it performs the job that you have asked for it to do. Otherwise it will give an error. So there should be a path by which you pass some parameters, and then there should be some way of returning or getting the results back from the OS. So this needs to be done, and there are some complications in it because OS is running in a protected mode or kernel mode. The other name for the kernel mode is a protected mode. In that case, it whatever you are passing needs to be accessed by this, of course, and then it should perform this job and then return some value. So what happens is, user, you know that when a function call is made and parameters are passed, they are passed through the stack. So the user stack, it is passed, whereas kernel has its own stack because it cannot expose its own operations to the user process. Because if suppose kernel is also writing into the user stack, when you return back in the user mode, I can go into the stack and then see what the kernel has done when I call the function, because you are indirectly leaking the way the kernel is performing the job, or you may be in fact leaking the some of the module addresses. Many things about the implementation of the kernel may be leaked if the kernel is using the user stack for its own operation. So there is a problem of security issue. So what normally happens is the kernel uses its own stack for its operations. When it is calling another function, it has to put the return address, right? That return address will indicate that where the kernel function is actually in the memory. So once that user process comes to know of this memory, it can try to access that memory by illegal means and try to tamper with that. So these are all well protected by handling or by providing a different stack for its kernel operation. So this transition of kernel stack and then copying the parameters passed in the user stack to the kernel stack, all those things need to be done. That's what I am showing it here. So there should be a wrapper function, because this wrapper function is implemented by the OS vendor or maybe the library person who is building the library, who is aware of the way OS is handling the parameters and how it is providing a mechanism to enter into the kernel mode. They are all captured in this wrapper function. It is implemented by somebody who is aware of this. So it's a system software. Wrapper function itself is a system software which is taking a gateway into the kernel mode or into system call. Okay, so they need to be aware of the processor sometimes, and how the stack is operating, and then how the kernel is maintaining its own stack, and what is the mode it is expecting the parameters to be passed to it, and how to take the result value from the kernel and pass it back to the user mode. So it's like a executive assistant to the president or a VC, where she or he is aware of the mode of operation of the person, and then what the user or the visitor wants to accomplish with the by meeting the VIP. So these are all the things which is to be handled by the wrapper function. Now, how is it handled? The best thing is to make it very reliable. Now, how can it be made reliable? You need to make it as an interrupt or a exception kind of a thing. Now, implementation. Now, what I mean by that? Now, suppose whenever I want to enter the kernel, I will, let me say that I am going to use an instruction called trap. It's equivalent to a software interrupt. What I mean by software interrupt is any interrupt that is coming from the external device, from the hardware device, a timer or a data arrival, that is called hardware interrupt, which is asynchronous to the execution of the program. Whereas software interrupt is one which is happening along in the execution itself. You are putting some instruction which is equivalent to a interrupt, which is called software interrupt, because you are embedding an instruction which will generate an interrupt, and it is in sync with the execution of instruction, because you can predict when it is going to be called, because you have only put the trap instruction. Maybe when I'm saying it, you means is a person who is implementing the wrapper function. So trap is a way by which the wrapper function takes the control from the user process to the kernel. Now, why is it done in this way? Because trap is a software interrupt, I said. How the interrupts are handled? Mostly they are some vector table, okay, interrupt vector table, which is in the kernel protected area, and it is based on the number you are giving. Maybe I will say trap some number, okay, XX. Then it goes to a predefined location in the vector table and then gets the address of the ISR, interrupt service routine. Now, who is filling this vector table? OS or the bootloader or whatever. And can user go and tamper with this interrupt vector table? No, because it is all in the protected area. Unless you are in kernel mode, you cannot even tamper with that. That means the entry point to the kernel is protected by means of making sure that the interrupt vector table is initialized by the OS before even any application comes up, and then protecting the area of the vector table to be in the kernel area. Okay, that means only if you are in kernel mode you can even tamper with it. Now, how will you get into the kernel mode? You have to execute the trap instruction, because default when you are executing the trap instruction, the transition from user mode to kernel mode happens. But once the user mode to kernel mode transition happens, you cannot execute anything other than the predefined routines, which is known to the OS and trusted software. That means the transition happens only when you execute the trap instruction. But when you are executing a trap instruction, it is going to take you to the routine which is already predefined by the OS. So I can't tamper with that and put my own code there. That way, it is well protected that nobody else can illegally execute their own instruction in the kernel mode. So it comes in. Now you may be calling any number of system calls, right? So what happens is normally a parameter is passed which will indicate what system call you want to actually execute, and based on the number you are passing, that system call will be executed. And then the return is also, there is a mechanism by which you can get back the results through some registers to the user process. That's very that's also the wrapper function comes into play and then passes the return value from the kernel to the user process. So it is normally in a register, predefined register. If it is an ARM, it's R0 register or R0 R1. No, it depends on the standard that is being defined by the particular vendor of the chip, Intel or ARM, and how the parameters are passed. Though I am saying that it is through stack, for efficiency purposes, they are also copied into the registers. You don't have to go to the stack to get the parameters. Now, predefined registers are there for some number of parameters, and if you are passing more than number of such parameters, they are passed through the stack. So this is not very important that you should know, but I am just sharing that information so that you are aware of how important it is to know how the parameters are passed and how it is implemented by the OS and the processor. Okay, now user process calls the system wrapper function, and wrapper function in turn executes the trap instruction which will be transitioning from user mode to the kernel mode, and then a particular procedure call based on what system call you are interested in calling will be executed, and by then the parameters are also available on either registers or in the stack based on the implementation of the system call. The kernel gets to know what the user wants it to perform, and then it also knows who is the user calling this routine, because process ID is there, and OS will know who has called this particular system call. Okay, then the software interrupt is generated, which is a trap instruction, and then it goes into the kernel mode. I think this is how it happens. I can tell you that trap is taking you to the predefined address which is initialized already by the OS, and it executes the ISR and exception return and comes back and it comes into the user mode. Okay, and some other system call, one more trap happens. Okay, it could be to the same ISR or a very different ISR. Okay, trap service routine. Trap service routine itself will call another function based on the parameter in one of the registers. So it's an interrupt which is software interrupt which is synchronous with the instruction being executed. The program execution jumps to the ISR, gets done, and then during that time, the PS process status word changes to the kernel mode and it executes. And then when it comes back, it returns back to the old. It saves the previous state of the status word, process status word of the process, user process, and restores it back. So when you come back, you are getting back to the user mode. So this is how a typical system software gets executed. Now in a typical Linux system call, what you do is you call a function, okay, a system call at the user level, which is calling, which is in fact a function defined in the wrapper function, and that calls in the x86, it is called int80. It's a software interrupt. It's not trap instruction. It's similar to trap instruction. And int 0x80 is an address in hexadecimal value, and it goes to that particular ISR vector, and then actual system call service routine is called, and then it executes it, which is this function goes there and returns, and then it comes back to the ISR. I return is a return from a vector, interrupt vector. So this is how the control is passed back to the user mode. During this transition, the kernel mode to user mode or user mode to kernel mode transition happens by preserving the PSW word status register content and modifying it to the kernel mode while going in, and then restoring it back the old value will take it back to the user mode. So this is what I have written it down. You can read it. So invoking system call is a particular system call is invoked by passing the system call number, and a software interrupt is generated, and parameters are passed through some system registers, and this invokes the system call handler, which is now transitioning from user to kernel mode. Corresponding C function call implemented in the kernel mode by the OS is called, executed, and returning from the system call, actual system call of the OS, coming back to the wrapper function. And when it comes back to the wrapper function, it is already changed to the user mode, and you come back to your own application. Now, whatever the kernel has returned is passed back to a register, and it gets to get back. No, it is given back to you as a return number, or it may be writing something into the one of the parameters that you have passed. If you have passed a address, and it will write into the addresses. So why use the API? Let me explain. Since system calls result in the execution of privileged kernel mode, it is supposed to be happening there. It would be crazy to let a user process call it directly. So a trap, because they are supposed to know about all the intricate details of how trap instruction works, how the parameters are to be passed to it, how to interpret the return addresses. These are all very cumbersome, and it's not that every user needs to know. So but as a system software developer, you are supposed to know, because I told you that system software interacts with the OS directly. Whereas as a user process, I don't need you to know about all these things. So that's why wrapper function is given, which will execute the trap instruction and jump to the kernel mode. Okay. Also, the API can allow the backward compatibility. Suppose if some changes happen with the OS implementation, because you know that Windows keeps updating it, and Linux also keeps releasing new releases or Ubuntu releases. Now, wrapper function is modified, then you don't need to worry about the which kernel version is running underneath. Your user application need not have to be recompiled, because once the wrapper function, I told you that wrapper function is part of the system software, which is also uploaded or updated along with the OS. So whenever OS changes, if there are any changes in the system form routine or parameter way it is the way it is passed, they are also reflected in the wrapper function. So user process doesn't have to know what are the changes happening in the implementation of the wrapper function, as long as the interface to the wrapper function is not modified. So your portability is also guaranteed, that whatever you have built earlier will still run, but the wrapper function is going to call, it's going to be a different library, and it's going to call the different way of interacting with the OS. So these are the advantages of having a wrapper function to interface with the OS. So entering the kernel mode is through an interrupt, you should know, and it is a safer mechanism to enter into a kernel mode, and it is also it also helps you that user processes need not have to know the intricacies of how the kernel mode or kernel system calls need to be called, how to pass the parameters, how to get back the results. They need not have to know, as long as the wrapper function is not modified or it is standard is maintained. So now if you are writing a vim, if you are using a editor vim, and then you are editing some text document. Normally you will be in user mode, but when you are handling some, you are typing some character needs to be written, read by the Vim application, then it gets into the kernel mode, reads a keyboard entry, and then comes back to the user mode. Okay, this is how system calls are called and interface. I think this is gives you a overview of what are the intricacies involved and how it is resolved, or how is it implemented in a real system like Linux or any other application. Bye bye. I hope you understood it and enjoyed this discussion. Let us meet you in the next section. Bye bye.